Okay, yeah, no, this is a zero cheating environment. All right, so here's the problem. A skier starts from rest at the top of a 45-meter hill, skis down a 30-degree incline. Oops, forgot to put that. It's 30 degrees, very important that you include that 30 degrees in there. And then continues up a 40-meter hill as shown. Neglect friction, no friction in this problem. How fast is the skier moving at the bottom of the hill? And what is the skier's speed at the top of the 40-meter hill? Now, by the way, we neglect friction, and of course in the real world there is friction. So what's the use of this problem? Well, what it does is it really gives us the maximum possible speed of the skier, right? I mean, and that's a useful thing to know. Hey, we know it'll at least be slower than this speed. And so I suppose if you're a ski racing coach, or if you're managing a ski resort or something and you want to keep it safe or want to know what rating to give a particular course, then that would be useful to know. Okay, so let's back out a little bit so I get room. Okay, so given, well, I already have I'm not going to redraw the sketch. We know this is 45 meters, 30 degrees, 40 meters, no friction. Yeah, so I'll just write given right there. And then what are we trying to find? I'll go ahead and put it down here. Find. Well, we want to know the velocity there. And I'll call this position 1. And this will be position 2 at the bottom of the hill. And this will be position 3. Just to make it easy to organize the problem. And this is for Carter. Okay. So, so we want to find the velocity at position 2 and the velocity at position 3. So that's what we're trying to find. That's for A and this is for B. So let's solve it. I guess we'll solve it over here. Now, the deal here is that the only force doing work on the skier is the force of gravity. And so that means that mechanical energy is conserved. And so I can say that E1 equals E2. The mechanical energy here equals the mechanical energy here. Now here, all of our mechanical energy is gravitational potential energy. So I'm going to go mg and then h, and I'll take a little shortcut and just say 45 meters is my height. And that's going to be equal to, well, down here, all my mechanical energy, well, my height is 0. So all of my mechanical energy got transferred into kinetic energy. And this is for part A. And so now, look, I got mass here, I got mass here. They cancel out. And so now I can just solve for V. So V is equal to 2 times G times 45 meters. And then you take the square root. And what do you get for velocity when you do that? What'd you get? 29.7?
Yeah.
Okay. All right. Okay, now for part B. Part B is a little bit more challenging. So let me do part B right next to it, or over here. Keep it on camera. Shh. So again, all the energy that we started with, none of it's there's no friction, so none of it gets dissipated into the environment. All the mechanical energy is conserved. So we can say that E1 equals E3. And so now we can say, okay, E1 again is mg times the 45 meters again is equal to, well, if you go up here, we've got height. So we've got mg 40 meters. Okay, we've got gravitational potential energy. But notice that we lost some height. So we also have to have a little bit of velocity. We have to have a little bit of our energy. It has to go somewhere. It's going to go into kinetic energy. And again, the masses are in every term, so they cancel out. Now, I'm going to do the algebra here. Let's subtract this to the other side. Factor out the g. You have g times 45 meters minus 40 meters. You see that? And then that's going to be equal to 1/2 v squared. And then I can multiply by 2 and take the square root. So v is going to be equal to the square root of 2 times g, which is 9.8 meters per second squared, or newtons per kilogram, if you prefer. And then 45 minus 40 is 5 meters. Now this 5 meters is also the change in height, isn't it? We changed height by 5 meters. And so we lost that much gravitational potential energy, and so it became kinetic energy. And so when you plug all those in, you get a velocity of a little bit slower, well, quite a bit slower. And what is it? What do you get when you do this? Anybody? Yes? What do you get when you don't round it to 10? 9.89. 9.89? We'll call it 9.9 or 10. Meters per second. Okay, Mia? Okay, and those are, and if you rounded this to 10, if you rounded this to 30, that's good. If you rounded this to 10, that's good as well. But the big picture here, come on, let's zoom out. Oh, let's zoom out as much as I can. Is that when you have a problem where there's no friction and the only force doing the only force doing work is gravity, then you can use this idea that the mechanical energy is just being transferred between potential energy and kinetic energy. And so you say, okay, the total mechanical energy here is equal to here. Anywhere, by the way, anywhere in this problem, I could put the skier right here. It doesn't matter. The mechanical energy of the skier is staying constant. Just that at the top of this hill, it's all gravitational potential energy. At the bottom of the hill, it's all kinetic energy. And when you're in between, it's being shared. Yes?
Why don't we use the angle at all?
Okay, sometimes you get a problem where you don't need to use the angle. It was superfluous. That's a good SAT word, by the way. Superfluous. In other words, it's something that you didn't need. It's
What kind of problems would you need to use the angle?
well, let's say that you were going to try and do this problem as if it was an inclined plane problem. That's when you would use the 30-degree incline. But notice that this hill, the way I drew it, the angle, like right here, might be 30, but it changes in between. So now here's a hint, okay? When you're trying to solve a physics problem, if you notice that the only force doing work is gravity, there's no friction, and what you're asked to find is a velocity, it's almost always easiest to solve the problem using energy, using conservation of mechanical energy. You could use, draw a free body diagram, use the procedure we learned a few months ago, and figure out what the net force is, and now you know what the acceleration is, and you can use the kinematic equations from there to find the final velocity. But that's a lot of work, isn't it? Whereas if you use conservation of energy, it's one step. That's why we use conservation of energy. It makes a lot of problems easier. And some problems, it's really the only practical way to solve it. I mean, like if I have this curving hill right here, Well, there might be a 30 degree angle somewhere, but it's not 30 everywhere. Okay? All right.